Okay, now picking up where we were last time and continuing on. So remember what we were doing was we were studying the excursion chain, and what the excursion chain was, it's a chain that's constructed from the we have it as usual a chain X on some state space, and it's moving around according to these transitions on this space X, script X. And what we do is we construct an excursion chain by keeping track of the paths that we've traversed away from a particularly designated state. And in this case, the state is just some generic state, script X, lowercase x. So what we do is that every time we visit the state, the excursion chain is just X. And then we append for each state, say, away from it. So let's say this is x1, this is x2, x3. What we would have in the excursion chain would be, we would go from x to xx1, xx1, x2, xx1, x2, x3, and then back to x, because every time we revisit x, we erase everywhere that we've already visited. Okay. So the transition probabilities from this chain, since it's constructed directly from a Markov chain on X, so X has transition probabilities P. We can define the transition probabilities Q of the excursion chain, and that's just in terms of the transition probabilities of the excursion chain, and that's just in terms of the transition probabilities of the if the X chain transitions to a state that's not X, then we're going to have a word with a bunch of Y's appended to it, a bunch of non-X states appended to it here, and then we transition to another state, which is just that excursion plus an extra state. And that's just with this transition probability here, because that's the probability that we would have made that transition in the X chain. Similarly, if we're in a state that has that looks like this, then we're going to transition back to X, just with this, the probability of going from the last state in the excursion to X, and so on and so forth. All right. And so what we showed was, well, this was left as an exercise, was that we could actually study properties of the chain X through this excursion chain by using this projection operation. All right, so the first thing that I want to show is that since we're interested in using these excursion chains to show something about the stationary behavior, the limiting behavior of the X chain, then we can actually compute what the stationary distribution of the excursion chain has to be in order for this approach to be useful. So the X excursion chain Y has a stationary distribution nu if and only if, first of all, X is positive recurrent for the chain X, and in this case we can actually write down what the stationary distribution has to be. We know that only states that look like this have positive probability of occurring in the excursion chain, and we can use an induction argument to show that this is what those probabilities have to look like. Okay, and in particular, so the transition probability of every state is a function just of the stationary probability of this special state X and the transition probabilities of P, which are given, get an explicit form for this in terms of the expected time that it takes to return back to X in the covering chain, the X chain. And to prove this, so how do we prove this? Well, one argument is to prove by induction and to think about, well, what would the stationary distribution actually have to look like if this were to hold at all? Okay, and so let's imagine such a stationary distribution exists. So if the stationary distribution exists for the chain Y, then it has to satisfy the usual condition, which is that the stationary probability for any given word is the sum over all other words in the space Y of stationary probability of that word times the transition probability. So this is by definition. Now, for any, so what we note though is that by the way that these chains evolve, for words that have length 2 or larger, there's only one candidate. There's only one state that is directly accessible in one step. There's only one state from which a given word is directly accessible in one step, and that's the word that is obtained by just removing the last element of the current state. So for any word with length bigger than 2, and the only word with length less than 2 is state X, is the word just X, because we know that everything has to start with X. For any word that looks like this, let's say we'll write it as this way. There is exactly one W prime such that this transition probability is strictly positive. So what we get in this case is that the stationary probability of a word W is equal to stationary probability of the word with one letter removed times the transition. But of course, that transition probability is just, in this case, we already know, this is the probability of transitioning from between the component, the next to last component, ym minus 1, and the last component. And so induction says that for words size bigger than or equal to 2, we know that this must hold. And now what we need to do is we need to compute actually what so this must hold if there's going to be a stationary distribution, and now what we need to do is we need to show that the stationary distribution itself has to satisfy the right, satisfies this condition here. Okay, so if these are the stationary probabilities, then what we know is that the sum over all the stationary probabilities has to be 1. So if such a nu exists, then we can sum over all of the possible excursions. So all possible excursions of length k, for k starting at 0, so an excursion of length 0 is just x. And this is, by definition, and what we just showed, what this has to satisfy, what the chain has to what the stationary distribution has to satisfy. And since these are probabilities, they have to add up to 1. Okay. But the thing to observe is that for each such k, this term here, this sum, this is the sum over all excursions of length k that don't revisit the state x. Okay, so every set of states in here time of time longer than k in which we didn't revisit x. Okay, so each one of these corresponds to the event that this is the probability, given that we started in state x, that it took at least time k to revisit x, because this is a sum over all possibilities. And so now we can easily see and we have a nu x out in front. Okay. So now what we can easily see is that this expression here, nu x, sum over all values k bigger than or equal to 0, tx bigger than k. And we know also that the amount of time it takes to revisit a state cannot equal 0. So this sum is actually equal to this one. And we've shown earlier that this is equal to the expectation. And we know that this has to equal 1. Okay. So that means that if nu x is going to equal anything, it has to equal 1 over this. expectation. And that this will only that this is only well defined, of course, in the case where this expectation is finite. Otherwise, it's going to be 0 for all values of x, because we know that x is we know that recurrence and transience are class properties. We've assumed that this is an have we assumed that this is an irreducible chain? We assumed last time this is an irreducible chain. These are class properties. So if one chain is recurrent, the others are recurrent, and vice versa. So if this is, we need this to be, if this is a positive recurrent state, then we know that this is finite and that this probability is well defined. And we get a proper stationary probability. Okay. So from this, we can actually immediately see a nice property of the chain X. So this is showing that the stationary distribution for Y has this expression. Okay. And so what we're actually doing is we're expressing the stationary distribution for the excursion chain in terms of the transition probabilities of the chain and some probability of being in state X. Okay. And what we can actually do is we can use this to infer, to actually deduce what the stationary distribution of the X chain has to be. So in the X chain, as a corollary, if X has a positive recurrent state, then it's going to have a stationary distribution. And that stationary distribution is going to be, it's going to coincide with the stationary distribution from the excursion chain in particular. Its probabilities have to satisfy this relationship. And the proof of this is going to make use of the fact, what's going on here? First of all, from the previous proposition, what we know is that the X excursion chain has stationary distribution. No idea what's going on. Has a stationary distribution with value pi x times the product over the transition probabilities for any given state. And this is where pi x here is the way that I've defined it up here. Okay, so pi x is defined right here. We know that this holds from the previous proposition. Okay. And we also have to note, or I'll claim, that the projection of f back into the state space X, that is a version of the original process. And remember, this was an exercise. So that should allow us to compute the the stationary distribution of the X chain in terms of the stationary distribution of the Y chain, since wherever the chain Y is at a given time projects to where X is, and we know that the behavior of X is determined by that behavior of Y. It coincides with it through this projection onto the last element. And so what we need to show, and this is also going to be an exercise, is that the induced chain, so the induced chain by projection on the last element, has a stationary distribution. And that stationary distribution is obtained by summing over all elements of Y that project down to X of the stationary probability. Okay. So why would this be true? Well, every time, if the chain, the argument goes that if the chain is stationary in the excursion chain, if the excursion chain is stationary, then the induced chain must be stationary. Okay, you're gonna have to make an argument there, but the argument there, which is an exercise, is going to be determined by the relationship between the stationary probabilities of the excursion chain and so the stationary probabilities of the excursion chain and the transition probabilities of the X chain. Okay, it's going to allow you to figure that out. And then once you figure that out, you're going to get this relationship. Okay, but then once you have this, once we have this, note that this inverse image of elements in the Y space that correspond to X is just X itself. So every time that the excursion chain is in state X, the X chain is in state X, and every time the X state is in state X, the Y chain is in state X. That's an equivalence, and that's because exactly that by the definition of this as an X excursion chain, we erase the entire excursion every time we revisit X. Therefore, if this relationship holds here, then the stationary probability of of the state X in the X excursion chain is going to be the stationary probability in the X chain itself. So this tells us then that this relationship here, mu X, is just equal to nu X, and this is equal to 1 over this expectation, and this was by the previous proposition. All right. All right. So, a couple more things to point out before we prove our main theorem. The main theorem being theorem 840, which we had back here, which said something about the which is a statement about the stationary distributions of positive recurrent Markov chains on finite state spaces, or on countable state spaces. All Now what we're going to do is, in this case, just make a couple of observations. Okay. What we're going to do now is we're going to recall, or stopping times tau, just to be find these stopping times to be the kth hitting time, the kth return time to x, from which we can define sequences of words. W1 is going to be the excursion starting at, if we start at x, the first state is x0. Well, the first state's always x0, and that would be x if we're starting at x. And we go up to the time just before okay. All right. Up to the time just before the first time we revisit, x. And then the second word is going to be started at the time of the first revisit. Okay. And so on. Kth defined in this way. All right. Then a quick lemma, two quick observations. First is that under initial distribution px, so if we start the chain in state x, these words are I, D, and under py, for y not equal to x, they are independent, and from W2 onward, they're identically distributed. Proof is an exercise, but I guess the question would be, how would you prove that? It's a pretty straightforward exercise, but you should think about that. And the second thing that we would like to observe, also as an exercise, is that if x is positive recurrent, for an irreducible chain x, then all states are positive recurrent. And a stationary distribution and pi x given by the expression 1 over the expected return time to x is a stationary distribution. So this proof's an exercise as well, but that's just to fill in the details, because intuitively, what do we know intuitively? Well, if a state's positive recurrent and the chain is irreducible, well, we know that recurrence is a class property, so all the states of the chain are then going to be recurrent. But then the question is, will all states be positive recurrent? So that's the first thing you have to show. And then, so intuitively, why would that be the case? Well, intuitively, that would be the case because since x is positive recurrent, we're going to return to x in a finite amount of time with probability 1, and the expected amount of time it takes us to return to x is finite. Every time we return to x, since it's irreducible, there's a chance we're going to then go and visit another state, say y, with positive probability before we return back to x. Okay. So since it takes us a finite amount of time to return back to x, and we have a positive probability of going to y before we return to x each time, then it makes sense that we have a probability, we have probability 1 of eventually hitting y, but we also expect to get to y in a finite amount of time. Okay. So that shows that all the states are positive recurrent. If all the states are positive recurrent, then this denominator here is going to be finite, and so all of these probabilities are going to be strictly positive, and they should be strictly positive because what we showed in an earlier, we made an argument earlier on in one of the previous lectures that if we have a positive, if a state x has a positive probability under the stationary distribution, and x communicates with y, then y is going to have a positive probability under the stationary distribution. So in this case, since all states communicate and they're all positive recurrent, they're all going to have positive probabilities under the stationary distribution. And we know also that we already showed that this is a stationary distribution for a positive recurrent state, and we showed that here. And so since it's a stationary distribution and it has that property, then we have this stationary property for this chain. All right. So now, next thing we want to do is we want to prove our main theorem. Our main theorem being that the theorem 840, that we can actually also express the stationary probabilities in terms of the long-run averages of how much time we spend in each state. Okay, so there's somehow an equivalence between the number of times we visit a state and the amount of time it takes us to revisit a state. Not unlike we saw similarly for renewal processes in Feller-Edwards-Pollard, that when we look at the long-run behavior of a renewal process, that the increment distribution, right? Well, the increment distribution was how big each step was, and we saw that the probability that we have a renewal at any given time is 1 over the mean of the increment distribution. So in that case, we had an equivalence between the probability in the long run of having a renewal at a given state, at a given time, and the amount of time it takes us to actually, well, the length of each renewal, or the times it takes for renewals to happen. So this is in the same vein as that. All right, so now the last thing that we want to show is we want to prove this last theorem here, theorem 840, about the limiting behavior, the long-run limiting behavior of positive recurrent Markov chains. And in order to do that, we're going to make use of a few things. We're going to make use of our excursion chains and also the observations that we made here that were left as an exercise about these sequences of words. sequences of words that are constructed using the sequential hitting times, tau k. Okay. So we're going to make use of that as well. All right. So in order to do this, let me first just make a definition. So the definition is that for a function f on the x space, let's define its additive extension on the y space, a space of words, by f plus, where every word has some, let's actually write this as every word is a string of some number of x's, and we define the additive extension just as the sum of the function f evaluated at these x's. Okay. All right, and so as a corollary, and this is where we're going to use those lemmas about the excursion sequences, which we showed, is that if we have a function f with additive extension f plus, then for any state in our state space x, we can compute the limit on k, averages of the function evaluated of the additive extension evaluated at these words wi, and that this has to equal the expectation, given that the chain starts at x, of the additive extension of just the first piece of the sequence. But we can define this then as, of course, this is the expectation, the additive. So f plus, remember this is just defined up here, but the length of the word is random. This is the length of a word of, say, of length 0, of length tau 1 starting at 0 of the function f evaluated at xj. Okay, and this holds with py probability 1 for all y, and in particular, really the key part of this is if we take f just to be the identity function, the function that's equal to 1, then this is just summing up. Then what's going on here? Well, this is the sum of 1 over the length of time of an excursion. Okay, so all that we observe here is that the limit k goes to infinity. So this is the length of the first excursion. This is the length of the, this is the time of the kth hitting time, the kth occurrence. And so we get that the limit as k goes to infinity is just given by this statement here. Okay. This is again with py probability 1. Okay. And the proof of this, which I'll leave to the notes, the proof of this is in the notes, but what we're making use of is we're making use of the strong law of large numbers, to using the fact that what we showed was that these W's are independent, and that except for the first one, possibly the first one, they're also identically distributed. So the strong law of large numbers is going to give us what we need in this case. Okay. And so now finally we want to prove theorem 840, which we have stated right here. So let me just put it up right here. So this is just saying that the number of visits to a state up to time n, that's given by n sub nx. So we need to show that if x is a positive, if the chain is irreducible, has a positive recurrent state, then there's a unique stationary distribution. So that if x is positive recurrent, so I didn't say this earlier, but if a chain is irreducible and it has a positive recurrent state, then we did show that all states, that recurrents are class properties, and if all states communicate and one of those states is positive recurrent, then all states are positive recurrent. So that allows us to call the chain positive recurrent in that case, and that's what we've been doing. But that's what justifies that that move. So if the chain, if x is positive recurrent, then it has a unique stationary distribution. Pi, such that the limit of the amount of time the chain spends in state x is the stationary probability, and this is with py probability 1 for all states x and y. And the other statement is that if this chain is null recurrent, then this limit is 0. I won't write that down, and then in both cases the chain is going to visit every state infinitely often. Okay. So to prove this, we note that, so to prove note by the previous corollary so what the previous corollary showed us is that if we had the expression that the time of the kth occurrence, the time of the kth passage, can be expressed roughly in terms of the expected amount of time of the first passage. Okay, so that the kth visit to a state x kth visit to x occurs approximately, kth visit to x happens at approximately time k times the expected amount of time it takes for the first return to happen. Okay. So again, this is just usual law of large numbers kind of thinking. Although you have to be a little careful here because of the dependence of the sequence, but the way that we got around that was by building up these excursions, showing that the excursions themselves are independent copies of one another, and using the law of large numbers that way. But this implies for large values of n, so if we have a large time n in the future, then what we might ask is, well, how many times have we visited state x by time n? Well, we know that each visit takes us about this expectation amount of time. And so how many chunks of that time have occurred up to time n? So this is approximately n divided by this expectation. And so what we already know is that from before, we already have that since this is a positive recurrent state, that this is stationary, that there is some stationary distribution that satisfies this. But we also know that this is equal to the limit of the amount of time the chain spends with py probability 1. And so what we want to show then is that this also, well, first of all, this also holds. So this holds for all y. And then so therefore, assuming that pi is stationary, so if pi is stationary, then we can express the stationary measure as an average over all initial, overall initial states. So then, since this limit holds with py probability 1 for each initial state, and since the stationary measure is just an average over all those initial states, it also holds with p pi probability 1. Okay. And the same is true for any initial distribution. Okay. So what we need to show finally is uniqueness. Okay. So uniqueness, we know that there's a stationary distribution with this property, but we need to have uniqueness. Okay. So finally, first of all, theorem here, we have an expectation, we have a limit here, and we want to show that the expectation of the limit is the limit of the expectations. That's no issue because these ratios are strictly between 0 and 1, so the bounded convergence theorem holds, allows us to conclude that the limit of this expectation also satisfies this condition. But we can also compute this expectation a different way, right? So the number of times we visit a state up to time n is a sum overall time points of how often of the indicators of whether or not we visited the state. Okay. And now we can bring the expectation into the sum, because this is a sum of indicators, and actually in this case it's a sum of finitely many indicators, so there's no issue there. And so what we're left with now is a sum j equals 1 to n of the stationary probability of being in state x. They're all the same, so this is just pi x. Okay. So what we must have then, since this property here is what we've already computed, is that this is pi x for all n, then this limit doesn't actually even depend on n, and so we get this expression. Okay. We get that pi x must equal this value for all x. Okay. So this gives us uniqueness, that if there's a stationary distribution, it has to satisfy this property. And so the conclusion that we draw here is that there is no stationary distribution if x is null recurrent. Because if x is null recurrent, these denominators would be infinite, and these stationary probabilities would be 0 for every state. So that's not a probability distribution. And there is a unique stationary distribution. If x is positive. Okay? And then we finally need to show that every state is visited infinitely often in either case. So in the case where it's positive recurrent, this is easy to show because the stationary probabilities are strictly positive. So since the stationary probabilities are strictly positive, and we have this relationship between the stationary probabilities and the number of times we visit a state in the limit, since they're strictly positive and the number of time points is infinite, then we must be visiting the state infinitely often with probability 1. But we can also show this is true, so the only thing we need to argue then is that it holds also in the null recurrent case, and we can do that by appealing back to these excursions. So in the null recurrent case, consider these W's. That we talked about earlier. Now these W's are independent, and they're identically distributed for sure if we just look at if we just look from W2 onward. And what this allows us to do is we know that since these are independent, we might be able to apply the strong law of large numbers. How are we going to do that? Well, since it's an irreducible chain, we know that every time we visit x, there's a positive probability that this excursion here will contain some state, say y. because all states communicate. So there's a positive probability that W2 contains an occurrence of Y. There's a positive probability that W3 contains an occurrence of Y, and so on and so forth. And so what we end up with is we end up with a sequence of such a sequence such as this. Each one has a positive probability of containing the state Y, and then from the strong law of large numbers, what we're going to get there is that each state gets visited infinitely often, even though the chain is null recurrent. So it has possibly an expected infinite amount of time until it revisits, until it comes back. We know that it will come back because it's recurrent, so we know that this sequence goes on. This W sequence goes on indefinitely. They're independent. Each one has a positive probability of seeing any given state by irreducibility, and so all states get visited infinitely often with probability 1. Okay. All right, so that's it for that theorem, and then we're going to come back, and then next time, when we do come back, we'll be talking about well, we'll probably be getting into, at that point, we're going to be getting into continuous time Markov chain.